How to draw the Bode plot. Bode plot, we have seen various types of frequency responses. One of them is Bode plot. Bode plot, we can draw the approximate frequency response without conducting any experiment. Just if we know the transfer function of any system, we can find the frequency response. We know that how it is difficult to find the frequency response experimentally. So that can be easily obtained if you know the mathematical model in terms of transfer function. The Bode plot means it has two parts. One is called magnitude plot, and another one is phase plot. We know that for a system G of S, if you give sinusoidal input with variable frequency, the output also a sinusoidal frequency of variable frequency. For every frequency, what is the ratio between input and output magnitude is called magnitude plot. For varying the frequency from 0 to infinity, and we are finding the output magnitude by input magnitude. If you find the ratio of output magnitude by input magnitude, and if you plot in decibel scale, x-axis is in logarithmic scale and the y-axis in decibel scale, then it is called magnitude plot. Phase plot is for different frequencies, for varying the frequencies, what is the phase shift in the output for every frequency? You will find, if you plot that, then it is called phase plot. Phase plot, that is in degrees. So there are two plots. One is magnitude plot, another one is phase plot. For as frequency varies from 0 to infinity, but constant input magnitude. If you assume it as a unity, then if we have to plot the magnitude plot is modulus of G of j omega. Is nothing but magnitude plot. Modulus of G of j omega, as omega varies from 0 to infinity, is called magnitude plot. Phase plot is nothing but angle of G of j omega, as omega varies from 0 to infinity. It's called phase plot. That we are going to do for various transfer functions. Suppose I'm having a transfer function G of S equal to K upon tau S plus 1 multiplied by tau 1 S plus 1, and suppose this is the transfer function. For that, we have to draw the frequency response. Means the first step is we have to find the frequency transfer function. We have to replace S by j omega. If you replace S by j omega, what you will get? J omega tau 3 plus 1 upon j omega tau 1 plus 1. J omega tau 2 plus 1. This we will get. Replace S by j omega. You will get frequency transfer function. For that, what is magnitude? Modulus of G of j omega, we have to plot as omega varies from 0 to infinity, means modulus of K is K. The modulus of this value is square root of imaginary part square plus real part square divided by square root of imaginary part square plus 1 square root of imaginary part square plus 1. So we got the magnitude. Here we have to vary omega from 0 to infinity, vary omega from 0 to infinity, and find this value and plot. That is called the magnitude plot. Phase plot is angle of g of j omega. Angle of g of j omega equal to, this is in one more point we have to consider. This is in linear scale. We are in need of logarithmic scale, decibel scale. So to convert this into decibel scale, 20 log k square root of omega square t cube square plus 1 divided by square root of omega square t1 square plus 1 square root of omega square t2 square plus 1. So log means multiplication become addition. Multiplication becomes addition. That's why it can be written as 20 log k plus 20 log square root of omega square t cube square plus 1 minus, it is in denominator. That's why minus square root of log 20 log square root of omega square t1 square plus 1 minus 20 log square root of omega square t2 square plus 1. So these are all. What is the advantage of writing like this? It is in decibel. Now it is in decibel. Earlier it is in linear scale. Now it is in decibel, dB. dB, decibel. The advantage is we can add for each factor. So if you know the plot for log k and 20 log square root of omega square t3 square plus 1, if you know the plot for these two, graphically we can add. Graphically we can add. In the same way, if you know the plots for each factor, we can add them graphically all together so that we will get the Bode plot. That is the advantage. How to add all these plots, that we will see later. So that is the method to find the magnitude Bode plot. It is very simple. If you know the transfer function, we have to deassemble like this. Then we have to find the plot quickly. Quickly we can draw. If you know the transfer function, quick rough plot or approximate plot, we can quickly draw. The approximate plot is called Bode plot. Similarly, we can find the angle also. What is the angle of g of j omega in the present case? K, what is that? G of j omega equal to k, what is that? Omega, j omega t3 plus 1 upon j omega t1 plus 1 multiplied by j omega t2 plus 1. This is the given sinusoidal transfer function. What is the angle of k? Angle of k is imaginary part is 0. Angle means tan inverse of imaginary part by real part. Tan inverse of imaginary part is 0. Therefore, angle of k is always 0. Therefore, angle of g of j omega equal to, for k, angle 0. For this, plus tan inverse of omega t3 divided by 1. No need to write that one. Omega t3 minus, because it is in denominator, tan inverse of omega t1 minus divided by 1 real part. No need to put. So tan inverse of omega t2 divided by 1. This is the angle plot. So we have to vary the omega from 0 to infinity. We have to get different values. We can plot without doing any experiment. We can find the phase plot as well as magnitude plot. That is called Bode plot. So what we have seen here is we can find the plot for each factor separately, and then we can add all together to get the complete plot. So what is the plot for each factor that we have to see? What is the plot for each factor that we have to see? So if we do the partial fraction, any transfer function, you will get k separately. You will get any pole at origin means, any pole at origin means that will be there. For that we can see the plot. Then any derivative factor in the origin, multiple, any s in the numerator, for that also we can plot. Then any first order factor in the denominator, j omega t plus 1, first order factor in the denominator. Similarly, first order factor in the numerator, for that what is the plot? Apart from that, it may be a multiple repeated poles, n and p, q, p repeated poles and q repeated zeros, like that. For that we have to see. Then it may be a quadratic, that is s square plus 2 zeta omega n s plus 1. If you write this in time constant form, it will be tau square s square plus 2 zeta tau s plus omega n square. If it write this in time constant form, it will be like this: tau square s square plus 2 zeta tau s plus 1. This is in natural frequency form. This is in time constant form. Always we use time constant form. Why? Because the gain k is correct only in time constant form. That's why always we have to take k. Whenever you want to take k, means the transfer function must be in time constant form, then only the k is correct. So we used to use time constant form for all plots. Other advantages are there for Bode plot that we'll see later. Time constant form. So if you write the second order transfer function in the time constant form, it may be this tau square s square plus 2 zeta tau s plus 1. It may be in the denominator or numerator. These are the fundamental factors you may obtain for a given transfer function. If you know plot for all these fundamental factors, you can draw the Bode plot. So let us see one by one how to draw the Bode plot for each factor. So first is, let us take k. Suppose g of s is equal to k, that's all. For that, what is the Bode plot? Magnitude plot is 20 log modulus of g of j omega. That is equal to, because g of j omega equal to what? G of j omega equal to k. Therefore, 20 log modulus of g of j omega equal to 20 log k. That's all. If you vary omega, k won't change. It is independent of omega. That's why for different values of k, what you will get, you have to check. If k is greater than 1, suppose k equal to 1, what you will get? 20 log 1 equal to 0 dB. If k equal to 1, if k equal to 1, if k is greater than 1, k is greater than 1, what you will get? Suppose k equal to 10, 20 log 10 equal to what? K equal to 10, 20 log 10 equal to 20 dB. You are getting, if it is k is greater than 1, if k is greater than 1, say k equal to 10, you will get a positive constant. Suppose k is less than 1, k equal to 0.1, what you will get? 20 log 0.1, that is equal to 20 log 0.1 to the 10 to the power minus 1. 10 to the power minus 1 is nothing but 0.1. 10 to the power minus 1 is 0.1. 1 by 10. 10 to the power minus 1 equal to 1 by 10, that is 0.1. So if you write like that, what you will get? A minus 20 log 10, that is equal to minus 20 dB. If k is 0.1, you will get minus 20 dB. K is greater than 1, let's say 10, you will get 20 dB. If k equal to 1, you will get 0 dB. What is the plot? Magnitude plot. The magnitude plot is log f. In the logarithmic scale, how you will put 0.1, 1, 10, 100, Like that you will write. Am I correct or not? Each division is 1 decade. 1 decade. That is called 1 decade. 10 times a fold of 10. If you multiply 0.1 by 10, you will get 1. If you multiply 1 by 10, you will get 10, like that. So fold of 10. What is the previous, before that, what will be there? 0.01. Before that, 0.001. It never reached 0 because log 0 is undefined. Log 0 is undefined. That's why there is no x-axis value 0. So 0.01, 0.001, like that it will go. So here, usually we start with 0.1. In a special cases, we'll start with 0.01 or 0.001, like that. Usually we start with 0.1, 0.1, 1, 10, 100, like that. Here, what is the value? Y-axis in dB, x-axis in log f. Log f we marked in Semilog sheet. In Semilog sheet, you have to buy Semilog sheet. Here, you will get 0. You will get 0. You will get 0 dB. 0 dB. That is k equal to 1. K equal to 10. K equal to 10. What you will get? Plus 20 dB. Plus 20 dB. If k equal to 0.1, you will get minus 20 dB. Minus 20 dB. When k equal to 0.1, you will get minus 20 dB. A horizontal line you will get. A horizontal line you will get. So this is the plot for k. What is the angle? Phase plot. What is the angle? Phase plot. What is the phase plot? Log f 0.1, 1, 10, 100, like that you will get. 1 hertz, 10 hertz, 100 hertz, 0.1 hertz, like that. Phase plot is for, it is only real part, no imaginary part. That's why always angle is 0. So the phase plot is 0 degree. 0 degree. Phase plot is like that. This is phase plot. Phase plot. This is magnitude plot. Magnitude plot. This is for k equal to 10, k equal to 1, k equal to 0.1. This is the magnitude plot for k equal to 10, k equal to 1, k equal to 0.1. And phase plot, whether it is k equal to 10 or 1 or 0.1, phase plot is same. For all values of k, the phase plot is 0 only, 0 degree only. Here, how we will mark frequency will be marked as 1, 10, 100, log f. Or you can write 1 can be written as 10 power 0, 10 power 1. Sorry, 1 can be written as 10 power 0, 10 can be written as 10 power 1, 100 can be written as 10 power 2, and 0.1 can be written as 10 power minus 1. Like that also you can write. Already we have seen that what are the factors in a transfer function. K already we have seen. And S in the denominator. S in the denominator. For that, what is the Bode plot? For each factor we will see separately, then finally we will add all together. So For that, 1 by S, G of S equal to 1 by S. For that, the sinusoidal transfer function G of J omega equal to 1 by J omega. Or it can also be written as minus J by omega. Multiply the numerator and denominator by J. You will get minus J by omega. What is modulus of G of J omega? Equal to 1 by omega. That's all. Modulus of G of J omega, how you will find the square root of real part square, 0 square plus imaginary part square, 1 by omega square, that is equal to 1 by omega. So we got, what is the angle? Angle equal to tan inverse of imaginary part. What is imaginary part? 1 by omega, that is imaginary part. What is denominator? Real part? Real part is 0. Therefore, that is infinity. Therefore, angle of G of J omega is, angle of G of J omega is always minus 90 degree. This is minus infinity. Minus infinity, that's why always minus 90. Minus 90. So angle always minus 90. But this will vary. Magnitude plot will vary. So how to plot that? Let us plot a rough plot for 20 log decibel scale. 20 log 1 by omega. G of modulus of 20 log modulus of G of J omega equal to 20 log 1 by omega. 20 log 1 by omega, when omega equal to 1, you will get 0. When omega equal to 1, 20 log 1 by omega equal to 0. Because 20 log 1 equal to 0. Omega equal to 10, what you will get? 20 log 1 by 10. That is 20 log 0.1. That is 10 power minus 1. That is equal to minus 20 dB. Minus 20 dB. Am I correct or no? When omega equal to 10, 20 log 1 by 10. That is equal to 10 power minus 1. That minus 1 will come here. That minus 1 will come here. Any power will come as product in logarithmic scale. Therefore, minus 20 dB. You will get log 10 equal to 1. Log to the base 10 we are using. So, minus 20 dB. When omega equal to 0.1, what you will get? 20 log 1 by 0.1, that is equal to 20 log 10. 1 by 0.1 equal to 10, that is equal to 20 dB. When omega equal to 0.1, it is 20 dB. When omega equal to 1, it is 0 dB. When omega equal to 10, minus 20 dB. So what is the plot? The plot is like this. The plot is like this. This is log omega. How we will mark 0.1, 1, omega equal to 0.1, 1, 10, 100, like that we will mark. So when omega equal to 1, what's its value? 0 dB. This is 0 dB. When omega equal to 1, you notice here, when omega equal to 1, 0 dB. That's why 0 dB. When omega equal to 10, minus 20 dB. Minus 20 dB. Here. So when omega equal to 10, minus 20 dB. When omega equal to 0.1, it is 20 dB. 20 dB. 20 dB. When this is omega equal to 0.1, this point is omega equal to 10. This point is omega equal to 1. So what you are getting? The plot is like this. The plot is like this. What is the difference between 0.1 and 1? 0.1 and 1. 20 dB. 20 dB. Difference between the magnitude change in 0.1 to 1 is 20 dB. Again, 1 to 20, what is the change? 0 to minus 20. Again 20 dB decreases. It decreases at the rate of 20 dB. 20 dB per decade. This width is called 1 decade. So it decreases at the rate of 20 dB minus 20 dB per decade. Like that we can write minus 20 dB per decade. Like that it decreases. So therefore, if we S in the denominator, a slant line it decreases at the rate of minus 20 dB per decade. That's all. We have to draw a horizontal, inclined line with a slope of minus 20 dB per decade. 1 decade means 0.1 to 1 is 1 decade. 1 to 10 is 1 decade. Because it is tenfold. If you multiply by 10, you will get the next. Multiply 0.1 by 10, you will get 1. If you multiply 1 by 10, you will get 10. If you multiply 10 by 10, you will get 100. Therefore, 1 decade. The slope is for 1 by S is, it decreases at the rate of minus 20 dB per decade. That's all. So what is the phase plot? Already we have seen that phase plot is because of real part is 0. Therefore, infinity we got always minus 90. Therefore, the phase plot is looking like this. If you draw the phase plot for this, this is the phase plot. Log F 1 10.1 omega equal to, this is omega equal to, or log omega, or simply you can write logarithmic scale, log omega you can write. Here it is always minus 9, always minus 9. This is the phase plot of 1 by S. This is magnitude plot of 1 by S. That's all. Suppose this is the, you see that this is omega equal to 1. Here omega equal to 0.1. Omega equal to 10. Omega equal to 100. So the magnitude, if you see, when omega equal to 1, 0. When omega equal to 10, you will get a minus 20. Minus 20. When omega equal to 0.1, plus 20. This is, the slope is minus 20 dB per decade. The phase plot, always minus 90 degree. Always minus 90 degree. Always minus 90 degree. Because real part is 0. Suppose I am having, instead of S, I am having G of S equal to 1 by S square. What you will get? G of J omega equal to what? G of J omega equal to 1 by J omega square. J omega square. What you will get? Modulus of G of J omega equal to modulus of G of J omega equal to 1 by omega square. Angle of G of J omega equal to what? Angle of G of J omega equal to 2 J omegas. For 1 J omega 90. For 2 J omegas 180 degree. So it can be written as 1 by J omega, 1 by J omega. For this for minus 90 degree, for this another minus 90 degree, therefore 180 degree. Or we can write 2 times tan inverse of imaginary part is omega, real part is 0. Therefore, minus, why minus in the denominator? So minus 2 times 90 degree, that is equal to minus 180 degree. The phase plot is always minus 180. If it is instead of, what is magnitude plot? 1 by omega square means 20 log modulus of G of J omega equal to 20 log 1 by omega whole square. that is equal to 40 log 1 by omega. 40 log 1 by omega. That can also be written as minus 40 log omega. Omega can be written as omega to the power minus 1. So if you bring that minus 1 as a multiplication factor, you will get minus 40 log. So when omega equal to omega equal to 1, what you will get? 0 dB. 0 dB. When omega equal to 10, when omega equal to 10, omega equal to 10, what you will get? Minus 40 dB. When omega equal to 0.1, plus 40 dB. Plus 40 dB. Because omega 0.1 equal to minus 1. So minus of minus plus, therefore 40 dB. So here, if it is 1 by s square means, what is the plot? 1 by s square means, here instead of 20, 40, here instead of minus 20, minus 40. That's all. The slope is minus 40 dB per decade. If it is 1 by s square. S cube means 3 times minus 60, 0, minus 60. Sorry, 60, 0, minus 60. Slope will be like that. So n means what? What is the, if it is instead of 2, n is there. So what you will get is 20 log modulus of g of j omega, when that is equal to 20 log n multiplied by, because g of j omega equal to 1 by j omega to the power n. So n times 20 log 1 by omega you will get. So we have to multiply. If you know 1 by omega, we can find any number. So just we have to multiply by that power. Just to multiply here. In this case, the power is 2. Therefore, 20 becomes 40. If power is 3, it becomes 60. Plus 60 minus 60. But anyhow, for omega equal to 1, always 0. Omega equal to 1, always 0. This is the plot for 1 by s. This is to know about plot. Already I told you that the distance between, this is 1, omega equal to 1. Omega equal to 1. This is omega equal to 0.1. This is omega equal to 10. Here omega equal to 100. Omega equal to 0.1. Omega equal to 1. Omega equal to 10. Omega equal to 100. What is the distance between these two? The distance between 0.1 and 1 is 1 decade. Already we have seen. 1 decade. Omega equal to 1 and omega equal to 10. The distance is called 1 decade. 1 decade. Therefore, the slope is mentioned as 20 dB. The slope here is minus 20 dB. Minus 20 dB per decade. That's why in 1 decade, the magnitude decreases by 20 dB. That's why the slope is called the minus 20 dB per decade. Here in 1 decade, here the value is 1. Here the value is minus 20. You notice that here the value is minus 20, here 0. But the distance between these 2 points is 1 decade. Therefore, the slope is minus 20 dB per decade. Decade means 10. So, yeah, multiplication factor of 10. That's why it is called 1 decade. Another scale is there, that is called the octal. Octal. 20 dB per decade and minus 6 dB per octal. Both are same. 6 dB per octal means the frequency will be doubled. Frequency will be doubled. Here it is 0.1. Here 0.2 doubled. 0.3. This is 1. This is 0.9. Here frequency is doubled. 0.4 means here frequency is doubled. So when the frequency is doubled, during this period, the frequency is doubled. What is the decrease in amplitude? Minus 6 dB. Therefore, 20 dB per decade as well as 6 dB per octal, both are same. Sometimes they may mention minus 6 dB per octal. So you should understand that both are same. Both are same. There are two scales. One is octal scale and decibel scale. 1 decade means multiplication of 10 frequency. Octal means doubled, twice, doubled. So octal scale means minus 6 dB per decade. Integral factors, that already we have seen. 1 by s power n means 1 by s power n means in decibel scale 20 log modulus of g of j omega equal to 1 by modulus of s power 20 log modulus of 1 by s power n. So that is equal to n times. So this can be written as 1 by s whole power n. Therefore, n times 20 log 1 by j omega to the power n. So j omega modulus of j omega to the power n that is equal to 20 log modulus of 1 by j omega to the power n. So n 20 log 1 by j omega, modulus of j omega is 1 by omega. You will get minus n 20 log omega. Therefore, you will get when omega equal to 1, 0 dB. When omega equal to 0.1, you will get plus 20. Because of 0.1, you will get another. Fractional number means negative. You will get another negative. Therefore, plus n 20 dB. N 20 dB. If it is 10 means, if it is omega equal to 10 means you will get minus n 20 dB. N 20 dB. If n equal to 2, what you will get? 40, 0, minus 40. N equal to 3 means 60, 0, minus 60 you will get. Bode plot at a derivative factor, 0 at the origin. That is g of s equal to s. For that, what is the Bode plot? G of j omega equal to g of j omega equal to j omega. Or it can be written as modulus of j omega equal to omega and angle equal to what? Imaginary part is omega. Real part angle equal to tan inverse of imaginary part is omega, real part is 0. Therefore, infinity. Tan inverse of omega infinity equal to tan inverse of infinity equal to 90 degree. You will get 90 degree. So angle always, angle of g of j omega always 90 degree. G of j omega equal to always 90 degree. Always 90 degree. So what will happen if omega equal to 0.1? When omega equal to 0.1, if we substitute that 20 log 0.1 equal to omega equal to 0.1 means you will get 20 log 0.1 equal to 10 power minus 1 minus 20 dB. Minus 20 dB. When omega equal to 1, 20 log 1 equal to 0 dB. When omega equal to 10, what you will get? 20 log 10 equal to 20 dB. So as omega increases, it increases. Therefore, the plot is when omega equal to 0.1, omega equal to 0.1 minus 20 dB. When omega equal to 1, 0 dB. When omega equal to 10, omega equal to 10, 20 dB. So it increases. Therefore, the slope is 20 dB per decade plus positive. 20 dB per decade, positive slope. It increases per decade. What is the slope? What is the phase plot? Phase plot already we have seen always 90 degree. Therefore, phase plot is 90 degree always for 0.1, 1, 10, 100, For all, you got 90 degree, always. Multiple factors. G of j omega equal to s power n. S power n. In that case, what you will get? Modulus of G of j omega equal to modulus of j omega to the power n, you will get. That is equal to, therefore, 20 log modulus of G of j omega equal to 20 log in dB scale, modulus of j omega, that is omega we can put to the power n, that is equal to n 20 log omega. When omega equal to 1, you will get 0. When omega equal to 0.1, you will get minus n 20. When omega equal to 10, you will get n 20. So we have to multiply by n. Slope is positive. If s in the numerator, slope is positive. S in the denominator, slope is negative. That's all. That is the only difference. But what is the phase plot? Phase plot is j omega. Suppose n equal to 2 means j omega multiplied by j omega. For this 190 degree, for this another 90 degree, therefore 180 degree. For n equal to 2, you will get 180 degree. N equal to 3, 270 degree, like that. What is the difference here? Plus 180 degree. 1 by s means minus 90 degree. S in the numerator means G of j omega equal to j omega means plus 90 degree. G of j omega equal to 1 by j omega means minus 90 degree. That is the difference. In the phase plot, that is the difference. We have seen construction rules for Bode plot. So far, only partially we have seen. Some more construction rules are there that we'll see today. So far, we have seen how to draw Bode plot for 1 by s, s in the numerator, and k. Now, let us see how to draw Bode plot for first order factor in the denominator. That is G of s equal to 1 by tau s plus 1. For that, how to draw the Bode plot, that we will see now. To draw Bode plot, the first step is we have to convert this into sinusoidal transfer function. Replace s by j omega. 1 by j omega tau plus 1. That is the first step. Then we have to find the magnitude. What is the magnitude? Modulus of g of j omega, that we have to find. That is equal to 1 by square root of imaginary part square plus real part square. This is magnitude plot. What is the magnitude? What is in decibel scale? That is 20 log modulus of g of j omega. That is equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square. For this, how to draw magnitude plot? We have to vary this omega from 0 to infinity. For that, we have to draw the magnitude plot. For that, we are considering two cases. The case one is omega tau is far greater than 1. Far greater than 1. And omega tau is far less than 1. Two categories. We are separating this into two cases. This equation is, for this we have to draw the Bode plot by varying omega from 0 to infinity. We are considering two cases. One is omega tau is far greater than 1. Another case is omega tau is far less than 1. If omega tau is far greater than 1, this is approximately equal to 1 is negligible. If omega tau is 1000 means 1 is negligible. Therefore, this can be written as minus 20 log square root of omega square t square. That is equal to minus 20 log omega tau. That's all. If omega tau is far, far greater than 1. Suppose omega tau is, this is for the case omega tau far, far greater than 1. That is case 1. In case 2, what we can say is omega tau is far, far less than 1. While compare with 0.001, let us assume 0.01. These are all negligible while compare with 1. That's why this can be written as minus 20 log omega tau is negligible because that is equal to 0.01 while compare with 1. Therefore, omega log minus 20 log 1, that is equal to minus 20 log minus 20 multiplied by 0. That's why 0 dB. So omega tau is far, far greater than 1 means the equation becomes minus 20 log omega t. If omega tau is far, far less than 1 means it is equal to 0 dB. 0 dB. Only 2 cases. Therefore, let us assume that when omega equal to 1 by tau, what will happen? When omega equal to 1 by tau, third case, when omega tau is less than equal to 1 by tau, we can replace omega tau by 1 by t. Therefore, it becomes, the equation becomes minus 20 log omega tau square root of omega equal to 1 by tau. 1 by tau square t square plus 1. T square getting tau square getting cancelled. Therefore, 1 plus 1, you will get 2. The third case is when omega equal to 1 by tau. When omega equal to 1 by tau, you will get the value 1. So, when omega tau is greater than 1 by tau, 1 is negligible. When omega is less than 1 by tau, when these two cases now we can define like this. When omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. Because when omega equal to 1 by tau, it becomes 1. When omega equal to 1 by tau, it becomes 1. Therefore, when omega is greater than 1 by tau, it comes under this category. When omega is less than 1 by tau, it comes under this category. So, this omega equal to 1 by tau is the point that differentiates these two cases. When omega equal to 1 by tau, it is equal to 1. That point is called corner frequency. Omega equal to 1 by tau is called corner frequency. That point is called corner frequency. Now, let us assume that G of j omega equal to 1 by square root of omega square t square plus 1. Already, first case is what? When omega tau is far, far greater than 1 means omega square tau square is far, far greater than 1. That's why we can ignore 1. Therefore, G of j omega becomes 1 by square root of omega square t square, that is equal to 1 by omega tau. Therefore, 20 log modulus of G of j omega equal to 20 log 1 by omega tau, that is equal to minus 20 log omega tau. Here, we are considering only the cases omega tau is far, far greater than 1. Therefore, 1 is negligible. We will get when omega equal to 10 by tau, what you will get? When omega equal to 10 by tau, What you will get? Substitute omega equal to 10 by tau. I said 1 by tau is the point at which it is called the corner frequency. We are moving away from that point. How many times? 10 times. 10 by tau. If you substitute omega equal to 10 by tau, this value equal to minus 20 log 10 by tau multiplied by tau getting cancelled. 20 log 10 equal to 1. Log 10 equal to 1. Therefore, minus 20 dB. Suppose omega equal to 100 by tau, what will happen? Omega equal to 100 by tau, what you will get? Then you will get minus 20 log 100 by t multiplied by t. Therefore, power 2. Therefore, you will get minus 40 dB. Minus 40 dB. What is the distance difference between when omega 1 equal to 10 by t, omega 2 equal to 100 by t, 1 decade away. What is the decrease in magnitude? 20 dB. Therefore, it decreases at the rate of, this is the 0.1. This is this is 1 by tau. This is 0.1 by tau. This is 10 by tau. This is 100 by tau. Suppose tau equal to 1, you will get conventional scale. Depends upon the tau value, you will get the scale like this. 1 by tau. What is the distance between these two? 1 decade. What is the distance? 10 times. Therefore, this is also 1 decade. Here at 1 by tau, after 1 by tau, at 10 by tau, its value is 20 dB. At 100 by tau, it is 40 dB. Therefore, it decreases at the rate of minus 20 dB per decade. It decreases at the rate of minus 20 dB per decade. Less than 1 by tau, it comes under this category. Less than 1 by tau, that is less than 1 by tau, it comes under this category. If less than 1 by tau, it comes under this category. Omega tau is negligible because it is fractional value. Less than 1 by tau means it is fractional value. Let us substitute. Omega is less than 1 by tau means let us put to 0.1 by t. If you put omega equal to 0.1 by t, t getting cancelled, 1 plus 0.1. 1 and 1 plus 1.1, both are almost equal. 1 and 1.1 are equal. Therefore, this can be ignored. This can be ignored when omega is less than 1 by tau. In that category, what you will get, that is left side of this point. Left side of this point, what you will get? 0, because 20 log, the magnitude is minus 20 log 1. Therefore, you will get 0 dB. Therefore, 0 dB. So, this is the plot for 1 by g of s equal to 1 by tau s plus 1. For that, this is the frequency plot. Suppose I am having like this, g of s equal to 1 by 5s plus 1. Tau equal to what? 5. 1 by tau equal to what? 1 by tau. This implies 1 by tau equal to 1 by 5. That is equal to 0.2. Therefore, the corner frequency is 0.2. Corner frequency is 0.2 radians per second. Tau equal to 5. Corner frequency is what? 1 by tau. 1 by tau equal to 1 by 5 equal to 0.2. Therefore, corner frequency is 0.2. 1 by 2 should be labeled as 0.2. Am I correct or not? 10 by t means 10 multiplied by 0.2. That is equal to 2. 100 multiplied by 100 by t means 100 multiplied by 0.2. That is equal to 20. Am I correct or not? So the plot is like this. Up to corner frequency, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Have you got? Still, you are having the confusion of 50. Corner frequency means 1 by tau. Corner frequency means omega equal to, we are assuming that omega equal to 1 by tau. At this point, 1 by tau means tau equal to 5. 1 by 5 means 0.2. Here, omega equal to 1 by 2, that is 1 by 5, that is equal to 0.2. Here, 10 by tau, that is 10 multiplied by 0.2, that is equal to 2. Here, 100 multiplied by 0.2, that is 20. Another example. G of S equal to 1 by 0.5 S plus 1. Tau equal to what? 0.5. What is the corner frequency? Corner frequency equal to 1 by 0.5. That is equal to 2. Therefore, the plot for this is, here, what is that? 0.1 by t. This is what? 0.1 by t. This is 1 by t. This is what? 10 by t. This is what? 100 by t. Now 1 by t equal to 2. Therefore, this becomes 1 by t becomes 2. This point is 2 radians. This is 20 radians. This is 200 radians. 200 radians per second. This is 0.2. Like that we can mark it. Because in the graph sheet, one division is what? 1 decade. So if you mark this as 0.2, this becomes 2. Therefore, up to 1 by tau, it is 0. After that, it becomes 0. After that, it becomes minus 20 dB per decade. After corner frequency, this is corner frequency. After corner frequency, it decreases like that. This is the frequency response for first order system. This is the frequency response for first order system. Suppose I am having 0.5 S plus whole square. Then what you will get? G of S, G of j omega equal to 1 by square root of 0.5 j omega plus 1. 0.5 square j omega square plus, omega square plus 1 whole square. That is equal to G of j omega equal to 1 by 0.5 square omega square plus 1. So in this case, modulus of. So if you square that, what you will get? You will get 1 by, let us assume 0.5 is tau. Generally, let us talk tau square omega square plus 1. Or what is the corner frequency? Omega equal to 1 by tau is the corner frequency. Before corner frequency, this is negligible. After corner frequency, this is negligible. Before corner frequency, tau square omega square is negligible. If you square 0.1, what you will get? 0.01. Therefore, squaring means then also it is negligible. Fractional value. Therefore, before corner frequency, this is negligible. After corner frequency, this is negligible. Therefore, what you will get is 20 log modulus of G of j omega equal to 20 log 1 by, let us assume t instead of 0.2 for convenience, generalized case, t square omega square plus 1, because G of S equal to 1 by tau S plus 1 whole square. Therefore, you will get like this. This becomes minus 20 log t square omega square plus 1. When omega tau is far greater than 1, case 1, this is equal to minus 20 log t square omega square. That is equal to minus 40. If you bring that square here, minus 40 log omega tau. If second case, if omega tau is far less than 1, what you will get? Minus 20 log t square omega square is negligible. That's why 1, you will get 0 dB. So up to corner frequency 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. Therefore, the plot is this is 0.1 by tau. This is 1 by tau. This is 10 by tau. This is 100 by tau. So up to 1 by tau, it is 0. After that, it decreases at the rate of minus 40 dB per decade. It decreases at the rate of minus 40 dB per decade. That's all. This is the plot for G of S equal to 1 by tau S plus 1 whole square. Suppose whole cube means it decreases at the rate of minus 60 dB per decade. Whole power n means it decreases at the rate of n multiplied by 20. Minus n multiplied by 20 dB per decade. Generalized case. Suppose now tau equal to, what we assumed, tau equal to 0.5. If you assume tau equal to 0.5, what is G of S? G of S equal to 1 upon 0.5 S plus 1 whole square. Therefore, this 1 by tau equal to 1 by 0.5 equal to what? 2. This becomes what? 0.2. This becomes what? 20. This becomes what? 200. That's all. That's all. Suppose tau equal to 10 S plus 1. 1 by tau equal to what? The corner frequency is 1 by tau equal to 1 by 10. That is equal to 0.1. Therefore, this point becomes 0.1. This is 0.01. This is, in that case, this becomes 0.1. This becomes 0.01. And this becomes 1. And this becomes 10. 10 S plus 1 whole square. So it decreases at the rate of minus 40 dB per decade. So now we know how to draw for first order in the factor in the denominator. Suppose the first order factor is in the numerator. First order factor is G of S equal to tau S plus 1 in the numerator. What you will get? G of J omega equal to J omega plus J omega tau plus 1. Therefore, modulus of G of J omega equal to square root of omega square T square plus 1. Omega square T square plus 1. Up to corner frequency. What is corner frequency? Omega equal to 1 by tau. If you substitute omega equal to 1 by tau, it becomes 1. If corner frequency is omega 1 by tau, if omega tau is far greater than 1, it means it is on the right side of 1 by tau. Right side of 1 by tau. Omega tau is far greater than 1 means omega is far greater than 1 by tau. You understand this point now? Omega is far greater than 1 by tau. Omega tau far greater than 1 means omega is far greater than 1 by tau. So that is the category 1. In that case, 1 is negligible. You will get modulus of G of J omega equal to square root of omega square T square, that is equal to omega tau. So 20 log omega tau means it is when omega equal to 1 by tau means 0 dB. When omega equal to 1 by tau. 20 log omega tau equal to omega equal to 10 by tau. You will get 20 dB. When omega equal to 10 by tau. When 20 log omega tau equal to 40 dB when omega equal to 100 by tau. So it increases at the rate of 40 dB per decade. It increases at the rate of 40 dB per decade. But up to corner frequency, that is second case is omega tau is far less than 1. That is omega is far less than 1 by tau. Far less than 1 by tau. Therefore, if any point is the left hand side of corner frequency, that is negligible. That is 20 log 1, that is equal to 0 dB. Any point is less than 1 by tau, it is negligible. Any point greater than 1 by tau is considerable. Consider and you have to draw. Therefore, the plot is 0.1 by tau and 1 by tau. This is 10 by tau. This is 100 by tau. Up to corner frequency 0 dB. After that, it increases at the rate of 20 dB per decade. It increases. Therefore, when G of S equal to tau S plus 1, this is the frequency response. It increases at the rate of 20 dB per decade. If suppose G of S equal to tau S plus 1 whole square, it increases at the rate of 40 dB per decade. It increase after 1 by tau, corner omega equal to 1 by tau, it increases at the rate of 40 dB per decade. Suppose G of S equal to tau S plus 1 whole cube, after 1 by tau, it increases at the rate of 60 dB per decade. Like that, it will increase. So, without hesitating, we can draw the frequency response for a first order system. If we know 1 by tau, that's all. If you know the time constant, that is corner frequency equal to 1 by time constant, corner frequency equal to 1 by time constant. After that, it decreases at the rate of 20 dB per decade. Before that, it is 0 dB. That is the rough plot. That is, or in other words, it is called asymptotic plot. It is called asymptotic plot. For example, I am drawing a plot for a first order system. The asymptotic plot is up to 1 by tau, it is 0. After that, it decreases at the rate of 20 dB per decade. It decreases at the rate of 20 dB per decade. What is the actual plot? This is asymptotic plot. We are ignoring omega t if it is less than, omega tau is far less than 1. If it is omega tau is far greater than 1, we are ignoring 1. If we consider both, what will happen? At corner frequency, what happens? That is equal to G of j omega, 20 log modulus of G of j omega equal to 20 log 1 by square root of omega square t square plus 1. That is equal to minus 20 log square root of omega square t square plus 1. That is equal to minus 20 log. If you consider both, at corner frequency, omega equal to 1 by tau. If you substitute omega equal to 1 by tau, what will happen? At corner frequency, this is the corner frequency. At corner frequency, I am considering both terms. This is 1 by tau square multiplied by tau square plus 1. That is equal to minus 20 log square root of 2. You will get minus 3 dB. If you calculate, you will get a minus 3 dB. Therefore, the frequency response, the actual plot is at this point, it decreases like this. Here, this is equal to minus 3 dB, 0 dB. Actually, up to corner frequency, we have drawn up 0 dB. But at corner frequency, there is an error of 3 dB. So, the asymptotic plot, that is the Bode plot. The difference between the Bode plot and the actual plot is, the difference between Bode plot and the exact plot is a difference of minus 3 dB only. A difference of, that too at corner frequency only. Other points, it is same, asymptotic plot. This plot is called asymptotic plot. Asymptotic plot. Because it is tangent at higher and lower values of omega to the actual plot. That's why Bode plot is asymptotic plot. It has an error of minus 3 dB at corner frequency. For a first order factor, it has an error of minus 3 dB at corner frequency. Suppose if it is a factor at numerator means here 0 dB up to corner frequency. Actual plot is it will be 3 dB at corner frequency. Therefore, the error at corner frequency is 3 dB. Error at corner frequency is 3 dB. If you are not ignoring both omega tau as well as 1, you will get minus 3 dB instead of 0. Therefore, at corner frequency, you will get only minus 3 dB or plus 3 dB error. If it is denominator factor, minus 3 dB. If it is numerator factor, you will get 3 dB error. So we can consider the approximate plot because of small error. Because of small error. Suppose if you want the actual plot means, you can do the necessary correction at corner frequencies. Necessary correction at corner frequencies. That's all. Let us consider a case g of s equal to k multiplied by tau 1 s plus 1 upon tau 2 s plus 1 multiplied by tau 3 s plus 1. For this, how to draw the Bode plot, let us see. Now, let us consider k equal to 1 and tau 1 equal to 10s plus 1. Here, we will get 5s plus 1. Here, we will get 20s plus 1. 20s plus 1. For k equal to 1 means 20 log k equal to 0. 20 log k equal to 0. That's why the plot for k is, when k equal to 1 means, the plot for k is at 0 dB, you will get a horizontal line. That's all. What is the plot for this 10s plus 1? What is the corner frequency for this? The corner frequency is 1 by 10. That is equal to 0.1. Let us say that this is 0.1, 0.01, 0.01. This is 0.1. This is 1. This is 10. This is 100. 1 by 5 is what? What is the corner frequency for this? 1 by 5. 1 by 5 equal to 0.2. What is the corner frequency for this? 1 by 20. 1 by 20 equal to how much? 0.05. 0.05. 0.05 is greater than 0.01. Am I correct or not? Okay. So everything is covered. So what is the plot for the numerator factor? What is the plot for the numerator factor? I am drawing the plot for numerator factor. Corner frequency is 0.1. Therefore, up to 0.1, it is 0. After that, it increases at the rate of 20 dB per decade. Am I correct or not? For this 5s plus 1, what is the corner frequency? 0.2. 0.2 is here. So 0.2 is here. Let us draw like this. To understand, let us put 0.1 here. This is 0.2. Corner frequency is 0.2 here. Corner frequency 2. This is corner frequency 1. This is corner frequency 3. Am I correct or not? I marked all these corner frequencies. Now I am going to draw the plot. The numerator, the corner frequency is 0.1. It is in the numerator. That's why up to 0.1, it is 0, approximate plot, asymptotic plot, Bode plot. Up to 0.1 is 0. After that, it increases at the rate of 20 dB per decade. It increases at the rate of 20 dB per decade. What is the plot for this? What is the plot for this? Corner frequency is 0.2. 0.2. Therefore, for that, it is up to 0.2, it is 0. After that, it decreases at the rate of minus 20 dB per decade. Up to 0.2, it is 0. After that, it decreases at the rate of 0.2, minus 20 dB per decade. The third case, 0.05 corner frequency. The third case is up to 0.05, 0, 0.050. After that, it decreases at the rate of minus 20 dB per decade. Am I correct or not? 3 plots I got. 4 plots actually. K equal to 1, that's why it is 0 dB always. 0 dB always. If you add all these 3 plots together, you will get the Bode plot for this. Bode plot for this you will get. You have to add all these together. This is for third factor. This is for second factor. This is for first factor. This is for first factor. This is for second factor. This is for second factor. This is for third factor. All the plots we have drawn separately, but we have to combine all these together. Here it goes up to infinity. It goes up to infinity. This goes up to infinity. This is also goes up to infinity. We have to add all these together. Up to 0.02, the second factor is 0. Up to 0.1, first factor is 0. Up to 0.05, third factor is 0. So after 0.05, some value is there. Am I correct or not? It is not 0. After 0.05, it is not 0. After 0.05, this factor is always there. I said it goes up to infinity. This factor is there. This factor is there. What is that? Third factor. The third factor corner frequency is 0.05. So after 0.05, this factor is always there. After 0.05, up to 0.05, it is 0. Therefore, we can draw like this. We can draw like this. So this is 0.05 for corner frequency 3. This is the corner frequency 3. Up to this, it is 0. Up to this, it is 0. After that, it decreases at the rate of minus 20 dB per decade because it is in the denominator. It is 1 by 20s plus 1. 1 by 20s plus 1. For that, the corner frequency is 1 by 20 equal to 0.05. Up to corner frequency, it is 0. After that, it decreases 20 dB per decade. Here, up to what point? Up to 0.1. Up to 0.1. Here, this is 0.1. Up to 0.1, it decreases at the rate of, up to 0.1, it decreases at the rate of 20 dB per decade. After 0.1, you see that what happens after 0.1, it increases at the rate of 20 dB per decade. One is increasing, another one is decreasing. If you add these two together, it becomes 0. One is increasing, the speed is positive direction. Another one is speed is in the negative direction. Both are equal. If you add it together, what you will get? 0. Therefore, no increase or no decrease. Am I correct or not? No increase or no decrease. Therefore, after that, it becomes horizontal. Why it becomes horizontal? For one factor, for this factor, it decreases. For this factor, after 0.1, it increases. Both are at same speed. One is increasing at the rate of 20 dB per decade. Another one is decreasing at the rate of 20 dB per decade. If you add these two speeds together, what is the speed? 0. There is no change in speed. There is no change in speed. That's why it remains in the same speed at 0 dB per decade. The slope becomes 0 dB per decade. Up to what? Up to 0.2 only. Up to 0.2 only. At 0.2, what happens? All the three graphs come together. What is the slope of this? Minus 20 dB per decade. What is the slope of this? Plus 20 dB per decade. If you add these two together, 0 dB. The third one comes into picture, minus 20 dB. Therefore, after this, again, it decreases at the rate of minus 20 dB per decade. Here, it is 0 dB per decade. Here, it is minus 20 dB per decade. If you add all these together, we got this plot. So this is the plot for the given transfer function. Suppose k equal to 10. Suppose k equal to 10. 10, what is the first? 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. Now, earlier k equal to 1. That's why you got a horizontal line at 0 dB. Now, k equal to 10. For what is the k plot? 20 log 10. That is equal to 20 dB. Am I correct or not? For k plot, it is 20 dB per decade. 20 dB. That's all. 20 dB. This is the plot for k. Now I change the sum. The second sum is k not equal to 1. It is 10. All other factors same. All other factors same. For all other factors, you got this graph. You combined all the three, you got this. Now you have to combine k also. K is equal to what? K equal to 20 dB. Here you got a line. This is 0 dB. This is 0 dB. 0 dB. This is 20 dB. Now we have to add this k with this. It means what? The entire graph will lift up by 20 dB. The entire graph will lift up by 20 dB. That's all. So here, the 0 dB, it starts at 0 dB. Instead, it will start here. After that, it comes down like this. Then it will be a horizontal line. Then it will. We shifted the entire graph by 20 dB. That's all. So, the k will shift the entire plot up or down. If k is greater than 1, it will shift the entire graph up. If k is less than 1, it will shift the entire graph by down. That's all. Now we got the Bode plot for 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. We got. This is the plot for k equal to 1. That is 10s plus 1 divided by 5s plus 1 multiplied by 20s plus 1. That is the difference. If k is there, if k is greater than 1, the entire plot will shift up. Otherwise, it will shift down. That's all. This is to understand what is happening in the Bode plot. What is happening in the Bode plot? You can draw, if a transfer function is given without doing any calculation. If you know the corner frequencies, you can draw the Bode plot. For example, in this sum, let us assume k equal to 1. What are the corner frequencies? What are the corner frequencies? Corner frequencies are 0.1, 0.2, 0.05. Am I correct or not? This is for 1 by 10. This is for 1 by 5. This is for 1 by 20. This is for denominator. This is also for, this is for numerator. This is also for denominator. Am I correct? 5 is for denominator. Am I correct? Yes. This is for denominator. This is for denominator. This is for numerator. So, if I know the corner frequencies, first corner frequency is 0.05. So, up to 0.05, it is 0. After that, up to 0.1, this is in the numerator. Up to 0.1, it decreases at the rate of minus 20 dB per decade. It decreases up to what point? Up to 0.1. After that, up to 0.2, it is horizontal line because both numerate. This is up to 0.1. It is in the numerator. At 0.1, it is in the numerator. Therefore, after that, it becomes horizontal. Again, up to 0.2, there are two terms in the denominator, one in the numerator. That's why 1 plus 20 and minus 20 getting cancelled. 1 minus 20 is there. Therefore, it decreases from 0.2. It decreases at the rate of minus 20 dB per decade. That's all. Now we will draw one k by 10s plus 1 multiplied by 0.1s plus 1. What are the corner frequencies? Corner frequency is 1 by 10. First corner frequency is 1 by 10, that is 0.1. Second corner frequency 1 by 0.1, that is equal to 10. First corner frequency is 0.1. Second corner frequency is 10. So I can draw the Bode plot. Let us draw the Bode plot for this. What is the Bode plot for this? What is the Bode? K equal to 1. Let us assume that K equal to 1. 1 minute. K equal to 1. For that, what is the up to 0.1? It is 0. After that, it decreases at the rate of minus 20 dB per decade. This is carries up to 10. Up to 10. Here, the corner frequency is 0.1. Up to 10, it is decreases at the rate of minus 20 dB per decade. After that, it decreases minus 40 dB per decade. Why? Why? There are another denominator factor. Here, it decreases at the rate of minus 20 dB. After 10 radians per second, another factor comes. That's why it decreases at the rate of minus 40 dB per decade. Therefore, this is the plot. Without doing any calculation, we can draw the Bode plot. Actually, this way we have to draw the Bode plot. For examination point of view, we need some data for the examiner. That's why we will see some systematic method to draw this Bode plot in the next class. So far, we have seen how to draw Bode plot for 1 by s, first order factor in the denominator, first order factor in the numerator, repeated poles and repeated zeros. In addition to that, we have seen first order system and first order factor in the denominator and numerator, that and all we have seen. Today, let us see how to draw Bode plot for second order system. Second order factor in the denominator as well as numerator. If you consider any transfer function, definitely there will be a gain. It may have poles at origin. It may have poles at zeros at origin. Both may not exist, but anyhow, both may not exist simultaneously. One will get cancelled the other. Definitely n minus m poles will be there if m is less than n. And the first order factor in the numerator and the first order factor in the denominator and the repeated factors, that also we have seen. Now let us see second order factor in the denominator, that is tau 3 s square tau square s square plus 2 zeta omega, 2 zeta tau s plus 1. This is second order factor in the denominator, or T4 s square plus 2 zeta tau s plus 1. Why this happens while factorizing means, if the poles are real, you will get the first order factor. The poles are complex, we won't convert into factor. In that case, we will keep it as second order factor. That's why if you factorize a given transfer function, the possibilities are These are the possibilities. For that, already we have seen 1 by s, s in the numerator, k, first order factor, repeated factors, that and all we have seen. Only pending is this. So g of s equal to 1 upon tau s square s square plus 2 zeta tau s plus 1. If this factor is there, what is the Bode plot that we are going to see today? If you convert this into sinusoidal transfer function, replace s by j omega, then what you will get? Minus omega square t square for this plus 2 zeta j 2 zeta tau omega plus 1. This you will get. What is modulus of g of j omega? Modulus of g of j omega equal to 1 upon square root of real part square, that is 1 minus omega square t square is the real part, whole square, plus imaginary part is 2 zeta tau, imaginary part is 2 zeta tau omega. So that square 4 zeta square tau square omega square, that is imaginary part. This is modulus of j of j omega. If you write this in decibel, 20 log 1 by, this is equal to 20 log 1 by square root of 1 minus omega square t square whole square plus 4 zeta square t square omega square. In dB, decibel scale. In that case, again, we will consider two cases. One is omega tau is far greater than 1. Omega tau is far greater than 1 means the zeta is always less than 1. Here, what you will get is omega power 4 20 log. This 1 becomes negligible because as omega tau is far greater than 1, that's why 1 becomes negligible. This becomes omega power 4 square root of omega power 4 t power 4 plus 4 zeta square t square omega square. This is also negligible. We'll compare with omega power 4 t power 4 zeta square t square omega square also negligible because fourth power is second power multiplied by zeta, that is less than 1. That's why this is also negligible. That's why this becomes that is approximately equal to 1 by 20 log 1 upon square root of omega power 4 t power 4 omega square t square. This is approximately equal to this. That is equal to 20 log omega square t square. If we bring to the numerator, you will get minus sign to the power minus 1. Therefore, minus 20 log omega square t square. If you bring this t square, if you write instead of omega square t square, if you write omega, this is also equal to minus 20 log omega tau whole square. Omega tau whole square. Therefore, this becomes minus 40 log omega tau. Now we will substitute omega equal to 1. Omega equal to 1 by t. If you substitute, what you will get? When omega equal to 1 by tau, if you substitute 1 by tau, this becomes 1. Therefore, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. When omega equal to 10 by tau, if you substitute 10 by tau, you will get 20 log modulus of g of j omega equal to minus 40 multiplied by 1, that is equal to minus 40 dB. When omega equal to 100 by tau, another 10 times increase, you will get 20 log modulus of g of j omega equal to minus 40 log 100 means 10 square, that is equal to minus 80 dB. Log 10 equal to 1, that square becomes multiplication, that's why minus 80 dB. So the slope is, it increases at the rate of 40 dB per decade. Another case is when omega tau is far less than 1. This 1 is considered, this omega square t square, this both are negligible. That's why 1 you will get. Root 1 is 1. Therefore 20 log g of j omega equal to minus 40 multiplied by 0 equal to 0 dB. Therefore, what is the plot for the second order? The plot is 0.1, omega equal to 0.1, 1, 10, 100 log omega, logarithmic scale. Here, let us assume that this is 1 by t, because we do not know the value of t. 100 by t, 0.1 by t. Up to 1 by t, it is 0. Up to 1 by t, it is 0. Up to 1 by t, it is 0. 0 dB. After that, it decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. If you find the error, what is, this is the plot. Up to corner frequency 0. After that, it decreases minus 40 dB per decade. If you consider complete 20 log g of j, modulus of g of j omega equal to 20 log minus 20 log square root of 1 minus omega square t square whole square plus 2 zeta 4 zeta square t square omega square. If you consider complete of this, it is function of zeta. It is function of zeta. Zeta value decreases, it is in the denominator. It is in the denominator. That's why as zeta value decreases, the magnitude will increase. The magnitude will increase. That's why the plot for zeta equal to 0.7 will be like this. The zeta for 0.7 will be like this. This is for zeta equal to 0.7. If you increase further, there will be a sluggish, maybe zeta greater than 0.7. If it decrease, what will happen? Suppose zeta is 0.2 means it will come like this. Zeta equal to 0.2. This is zeta equal to 0.5. Like that. So there will be a large error at corner frequency for second order system. That is the only drawback. Anyhow, for 0.7, it gives approximately this value. If zeta equal to 0.7, it gives almost minimum error. Suppose if you have a second order factor in the numerator, that is what g of j omega equal to g of j omega equal to g of j omega equal to tau square s square plus 2 zeta tau s plus 1. if you give like this, then what is the plot is just opposite to this. Here, it decreases at the rate of minus 40 dB per decade. Instead, it will increase. Therefore, the plot will be like this. Up to 1 by tau, it is 0 dB, 0 dB. After that, it increases at the rate of 40 dB per decade. This is second order factor in the numerator. Here also depends upon the zeta value. It will be like this. This is for 0.7. Zeta equal to 0.7. If zeta decreases, you will get like this. If zeta increases, you will get lag value. So error will be minimum when zeta is around 0.7. So approximate plot is this: up to 1 by tau, 0. After that, it increases at the rate of minus 40 dB per decade. That's all. We have seen all factors. Hereafter, we can draw Bode plot for any function. Before going that sum, the procedure to draw Bode plot, let us consider this g of s equal to k and tau s plus 1 and tau square s square plus 2 zeta tau s plus 1 upon s, then tau 1, tau 2, tau 3 s plus 1. This is tau 4 s square plus 2 zeta tau 4 s plus 1. 4 time constants are there. Let us assume that T1 is T4 is greater than T2 greater than T3 greater than T1. Which is the smallest value? T1. T1 is the smallest value. Therefore, largest corner frequency is 1 by T1. Omega 4 equal to 1 by T4. Omega 2 equal to 1 by T2. Omega 3 equal to 1 by T3. Omega 1 equal to 1 by T1. If you write in terms of omega, omega 4 is the smallest. Omega 2 next. Then omega 3 next. Omega 1. Which is the largest? Omega 1 is the largest. So, what is the plot? Let us mark all the corner frequencies first. Omega 1 is largest. Therefore, first will be omega 4. Next will be omega 2. Omega 3. Then omega 1. Am I correct or not? Whether I correctly marked? Correctly marked. Except k, all other. One more is s is there. Except k and x, I marked all for all factors. Omega 4 is what? For T4. Omega 4 is for T4. What is the corner frequency for this? What is the corner frequency for this? For this corner frequency is omega 4. Therefore, for this up to omega 4, it is 0. Am I correct or not? Up to omega 4, it is 0. After that, it decreases. It will decreases at the rate of minus 40 dB per decade. Minus 40 dB per decade. It decreases at the rate of minus 40 dB. Minus 40 dB per decade. Because it is second order factor. That's why it decreases. But we can extend up to omega 2 only. Omega 2 is where? In the numerator. What is its slope? Plus 40 dB. That's why omega 2 to omega 3, again it will be horizontal line. Again it will be horizontal line. Omega 3 is again in the denominator, but first order factor. That's why it will decrease at the rate of 20 dB per decade, minus 20 dB per decade. It will go up to omega 1 only. At omega 1, again numerator factor. That's why 20 getting cancelled. Again it becomes horizontal. Again it becomes horizontal because for this 20 dB plus 20 dB per decade, for this minus 20 dB, for this minus 40, for this minus 40. So all equal, plus 40. This is plus 40. That's why all equal, that's why getting cancelled. Finally, it becomes horizontal. Suppose more denominator factor means finally it will decrease, further decrease. We plotted, if you know the corner frequencies, we can draw the Bode plot without doing any calculation. Now, how to incorporate K and the S? How to incorporate K and S? What is K? For K is 20 log K in dB scale. In dB scale, 20 log K. 20 log K, K equal to 10 means it is 20 dB. 20 dB. This is the plot for K. This is what? 0 dB. Therefore, 20 dB will be here. 20 dB will be here. 20 dB. This is plot for K. This is plot for K. 20 dB. K equal to 10. That's why 20 dB. 1 by omega, 1 by S. For that, what is the plot? It is inclined at minus 20 dB per decade for the entire plot. Minus infinity to plus infinity, it decreases at the rate of, we have already seen, it decreases at omega equal to 1. At omega equal to 1, it crosses 0 dB. That is the only point that we know. When omega equal to 1, 1 by S means what? 1 by 1, 20 log 1 equal to 0, therefore 0. It decreases at the rate of 20 minus 20 dB per decade. This is for 1 by S. I am writing a plot for 1 by S also. Let us assume that omega equal to 1 is here. Omega 4 is less than 1. Let us assume. Therefore, this is the plot for 1 by S. 1 by S. We have to add these three together. If we add these three together, we will get the complete plot. So I am telling you how to, if you know the transfer function, you can draw the frequency response. So for K, you have to lift everything by 20 dB. You have to lift everything by 20 dB. Therefore, 0 dB becomes 20 dB. Am I correct or not? If you lift the entire plot by 20 dB up, you will get 0 dB becomes 20 dB. That's all. So we included K. The only thing is we have to include that 1 by S. If we include 1 by S, what will happen? This horizontal line is, the slope is 0 dB per decade. But because of this, it becomes 20 dB per decade. Therefore, this becomes, this 0 dB becomes minus 20 dB per decade. This 40 dB becomes minus 60 dB per decade. This horizontal line again becomes minus 20 dB per decade. This minus 40 becomes, this 20 becomes minus 40. This horizontal line again becomes minus 20 dB per decade. The slope is now changed because of this 1 by S. The slope is changed. The slope is changed. So what we have to do is, now we have to shift this up by, so here we have to draw L. Here already this is shifted for 20 dB. Here instead of horizontal line, we have to draw yeah, 20 dB line. 20 dB line. Again, this becomes 60 up to omega 2. Again, this is 20 dB line. Again, this becomes 40 dB. This becomes 40 dB. Again, 20 dB. Like that, the slope will be changed, 1 by S. The slope will be changed. So instead of horizontal line, its slope is minus 20 dB per year. Instead of 40 dB, it becomes 60 dB. So for the entire plot, we have to add 20 dB. So we can draw the rough plot. we can draw the rough plot. So how to draw that, we'll see here. 1 by k by s we have to take. That k by s is, if you draw only for k by s, for k it is 20 dB, 1 by s at omega 1 equal to, you will get a 20 dB slope at, this is for 1 by s, its slope is minus 20 dB per decade. This is 0.1. That's why for k you will get a line here. For k equal to 10. That is 20 dB. If you combine these two, what will happen? If you add 20 dB at every point means this will shift up to by this, like this. This is 10 by s. Am I correct or not? This is 10 by s. Now we have to add the previous. This is omega 4. Omega 4. This is omega 2. Am I correct? Omega 2. This is omega 3 and this is omega 1. Now we have to add that previous plot. This has to be added. This is 40 dB up to omega 2 and then horizontal, then 20 dB, then horizontal. Now we have to add this and this. One more time we are seeing, that's all. So here, this is horizontal, this is inclined line. That's why this we have to take, that's all. This we have to take up to omega 4. After omega 4, what is the total slope? This is 20 dB, this is 40 dB, minus 40 dB per decade, because second order factor. This is 20 dB. Now we have to draw up to omega 2, 60 dB per decade. So up to omega minus 60 dB per decade. After this, what will happen? This is 0, but this is 20 dB. That's why from omega 2, we have to draw only 20 dB, minus 20 dB per decade. Up to omega 3. At omega 3, this is 20. This is also 20. Therefore, we have to draw at 40 dB. We have to draw at minus 40 dB per decade line up to omega 1. After omega 1, only 20 dB. Only minus 20 dB per decade. So, if you know k by s separately and all other factors separately, just we can add like this. So, this is, you should learn how to draw rough frequency response for given transfer function. But for examination, there is a procedure, because they may expect if you draw directly, how the mark will be given. That's why we have to draw a table and how we are adding that and all we have to tell. That we will see now. First, step 1, to draw Bode plot, step 1 is convert the given transfer function into time constant form. Because already I told you that in time constant form only k will be correct. K will be correct. Therefore, the first step is we have to write in the time constant form. For example, g of s equal to 1 by s plus 5 is given. How to write this in time constant form? We have to take that 5 outside. So what you will get? 1 by 5 s plus 1. 1 by 5 s plus 1. 1 by 5 s plus 1. Therefore, the transfer function becomes 1 by 5 divided by 1 by 5 s plus 1. This is time constant form. Therefore, earlier in this form, what is the gain? 1. It is not correct. The actual gain is 1 by 5, 0.2. Therefore, we have to write, the first step is we have to write in time constant form. Step 2. Step 2 is convert into frequency transfer function. Convert the given transfer function into frequency transfer function. That is s equal to j omega. You have to substitute s equal to j omega. Then the next step is Step 3. Find the time constant form in factorized form. Definitely they will give in factorized form. They won't give 10 s power 5, s power 6. They won't give because you cannot factorize. That's why they will give automatically factorized form. If it is not factorized, you have to factorize. But it's very difficult to find the roots. That's why they won't give like that. If it is given, you have to find. But in factorized form, then the third step is find the corner frequencies. Corner frequencies. After finding corner frequencies, we have to draw a table. We have to form a table. The first column is given factor. Second one is corner frequency. Third one is slope contributed by the factor. This factor. I will explain what is that. Slope, then slope contributed by the given factor. This factor. In this case, the factor is 1 by 5 s plus 1. That is the given factor. Then net slope means as the corner frequency increases, what happens? The previous slope is added to the next slope. That's what we have seen. That the diagram is not there. So initially it is minus 40 dB. After that it becomes 0 because we are adding minus 40 and plus 40. Then again it becomes minus 20. Again it becomes 0 slope. So that is called net slope. Then frequency range are coordinates. The coordinates. That's all. The first factor is k by s. No corner frequency for 1 by s. Therefore, we have to put a dash. The slope contributed by the factor is minus 20 dB per decade. Am I correct or not? Or you can put the unit here, dB per decade, and you can put simply minus 20. Net slope minus 20 dB. Before that, no factors. That way. Now we have to find the coordinates. Second one is, suppose I am having a denominator factor 1 by 0.2 s plus 1. 0.2 s plus 1. Then what we have to do? Corner frequency is 0.5. Am I correct or not? Corner frequency is 1 by 0.2, that is 5. Slope contribution is minus 20 dB. Net slope is minus 40. Then third factor, suppose it is in the numerator, 0.02 s plus 1 in the numerator. What is the corner frequency? 1 by 0.02. How much? 50. Therefore, the corner frequency is 50. The slope contributed is minus 40. It becomes minus 60. Huh? Oh, plus 20. Very good. Plus 20. That's why plus minus 20 again. Again minus 20. Suppose I am having a next factor is around 100. 100 means 1 by 100 equal to 0.01 s plus 1 in the denominator. So the corner frequency is 100. Slope is minus 20. Slope contributed by this is minus 20. What is the net slope? Minus 40. That's all. Now we have to find the coordinates. That's all. If you find the coordinates, you can immediately draw the root locus. What is the smallest corner frequency? 5. Smallest corner frequency is 5. That's why we can take a scale. From 0.1. I told you that no corner frequency is less than 0.1 means take from 0.1. Scale, x-axis scale must be taken from omega equal to 0.1. This is 1. This is 10. This is 100. This is 1000. Log omega scale. Now we have to find the coordinate at omega equal to 0.1 for the first case. Because we started where? 0.1. What is that factor? K by S. What is G of S equal to K by S? Am I correct or not? Let us assume that K equal to 20. Let us assume that 20 by S. Because everything we took number, that's why let us take 20 by S. Therefore, 20 by S. What is G of J omega? G of J omega equal to 20 by modulus of G of J omega. 20 by omega. 20 by omega. What is 20 log? 20 log modulus of G of J omega equal to minus 20 log plus equal to 20 log 20 by omega. Omega equal to 0.1, substitute and find the value. Substitute 0.1 for omega and find the value. 20 log 20 by omega. Minus 46.0. Okay. Definitely positive because 20 by 0.1 greater than 1 plus only. Minus 46. 26, 20. Okay, 46 is correct. Minus 46. Y coordinate is 46. What is the x coordinate? What is the x coordinate? 0.1, comma 46. I got the coordinate. Now let us find the second coordinate. Coordinate at this row. Let us find coordinate for this row. First row we find the coordinate. 0.1, comma 46. Next coordinate, we know the equation for, what is the equation for straight line? y2 minus y1 equal to slope multiplied by x2 minus x1. This is equation for straight line. These are all straight lines. That's why we can write equation like this. Therefore, y2 minus y1 equal to slope multiplied by, this is in logarithmic scale. That's why log x2 minus log, not x2, log omega 2, log omega 1. Therefore, you will get y2 equal to slope multiplied by log omega 2 by omega 1. Because log omega 2 minus log omega 1 equal to log omega 2 by omega 1 plus y1. Plus y1. Am I correct or not? This is the equation. By using this equation, we can find the coordinates. Where we have to find the coordinates? At corner frequency 5, we have to find. Therefore, we know the x coordinate. We know the x coordinate. Only thing is we have to find y coordinate. What is the formula? y2 equal to slope. What is the slope for this? Because after corner frequency 5 only it becomes 40. After corner frequency only it becomes 40. Before corner frequency, up to corner frequency it is 0 slope. That's why whatever the previous factor slope only it will contribute. That's why minus 20. Therefore, y2 equal to, we have to find y1 equal to what? 46. Am I correct or not? y1 equal to 46. Omega 2 equal to 5. Sorry, omega at 5 we have to find. Omega 2 equal to 5. Omega 1 equal to 0.1. Am I correct or not? y1 equal to 46 because this is omega 1, this is y1. Now we have to, this is omega 2, y2 we have to find. y2 we have to find. Therefore, y2 we have to, in question, y1 is 46, omega 1 is 0.1, omega 2 is 5. Therefore, just to substitute this y2 equal to slope. That is, only thing is you have to use this slope. This slope, previous slope we have to use because up to 5 only we are finding. Therefore, minus 20, the formula is slope multiplied by log omega 2 is 5 divided by 0.1 plus 46. Find 12.0 because log 50 is 1.6 you said, multiplied by 10, 16, multiplied by 2, 32, 46 minus 32 how much? 14, rough calculation 14, so 12 will be correct. So y2 equal to 12, therefore the coordinate is the 5 comma 12, that's all. Now we have to find the next coordinate. Next coordinate we have to find. Then what is this is omega 1, this is y1. Omega 2 equal to what? Omega 2 is 50. Omega 2 is 50. This is omega 2. This is y2. That's all. Find y2. y2 equal to, let us call this y2. The latest value is y2. You should remember like that. y2 equal to, what is the slope? Previous slope? To calculate this, we have to use this slope. Previous slope always you have to use because up to 50 only we are finding. Up to 50 only. After 50 only, this factor will contribute. Why I am telling like that? This factor will contribute after corner frequency only. That's why that value we should not take. Previous value we have to take. So minus 40 log, that is omega 1 is 5, omega 2 is 50, therefore 50 divided by 5 plus y1 is 12. Find that. Minus 28. Log 10 is 1. 50 by 5 is 10. Therefore, minus 40 plus 12. Minus 28. Minus 28 dB. Therefore, the coordinate is 50, comma minus 28. Now we have to find the coordinate for the final. Again, we have to consider this as omega 1. This is y1. Omega 2 is what? Omega 2 is 100, comma y2 we have to find. Therefore, we can write y2 equal to, what is the slope? Previous slope we have to find. What is the previous slope? Minus 20 log 100 divided by 50 because omega 1 is 50. Omega 2 is 100 plus y2 is minus 28. What is the value? Minus 34. Minus 34. One more coordinate we have to find because we found up to 100 only. One more coordinate we have to find. After that, what is the slope? 40 dB per decade. Therefore, we can write after 100, what is the next decade? 1000, comma, add 40, minus 74. That's all. Minus 74. Because after that, it decreases at the rate of minus 40 dB per decade. Therefore, we can write like that. Now we have to draw the Bode plot. What are the coordinates? 0.1, 46, 5, 12, 50, 28, 100, 34, 1000, 74. That's all. We have to draw the Bode plot. What is the first coordinate? 0.1, 46. 46 dB. Then at 5, 12, at 5, 12, maybe 5 here. It is 12. At 5, this is 5, 12. Next one is minus 28 at 50. 50 means here. Minus 28. Maybe around here. Minus 28. Minus 28 at 50. Then minus 3400. At 100, minus 34. Maybe here. Minus 34. At 1000, it is 74. So it is here. At 1000, minus 74. Minus 74. So we have to join all these lines. So this is the magnitude plot, Bode magnitude plot. That's all. So it is very simple. No need to understand anything. We have to fill this table. That's all. The first factor is if K alone is there, we have to write K alone here. K alone you have to write. If S or S square is there, we have to substitute. That's all. This first factor is K by S power N or K S power M. Suppose numerator factor alone is there. So all S factors, any pole or zero at origin must be combined with that, the first. All other factors, you have to write like that and fill the table and draw the Bode plot. Magnitude plot is over. What is the phase plot for this? What is the transfer function? The transfer function G of S equal to K, these two, 0.2 S plus 1. This is 0.01 S plus 1. This is 0.02 S plus 1. This is the given sum multiplied by S. Am I correct? So we have to write to find the phase plot G of j omega equal to K 0.02 j omega plus 1 whole divided by j omega 0.2 j omega plus 1 0.01 j omega plus 1. What is the angle of G of j omega? Angle of G of j omega equal to K is 0 always. Angle for K is 0. That's why we can leave. For remaining thing, this is a numerator. That's why tan inverse positive plus tan inverse of 0.02 omega minus tan inverse of 0.2 omega minus tan inverse of 0.01 omega minus 90 degree. For this j omega, only imaginary part, that's why minus 9. That's all. Substitute omega equal to 0.1. Here, substitute omega equal to 0.1, find the angle. Then substitute omega equal to 1. Always you have to find it for omega equal to 1. So substitute omega equal to 1 and find the angle. Substitute omega equal to 5, find the angle. Substitute omega equal to 50, find the angle. Substitute omega equal to 100, find the angle. Substitute omega equal to 1000, find the angle and draw the phase plot. The phase plot will be like this. If we draw, it will be like this. So the final angle will be these two getting answered minus 180. The maximum angle will be minus 180 degree. The minimum angle is so you'll get substitute get some 4 or 5 values between 0.1 and 1000. 0.1, what is the angle? when omega, you form a table like this. A table like this. This is omega, angle of G of j omega. 0.1 we have to find, then we have to find for 5, then you have to find for 50, 100, 1000. And omega equal to 1 also you have to find. So I forgot. So omega equal to 1, omega equal to 0.1. This is omega equal to 0.1. 0.1, 1, 5, 50, 100, 1000. You substitute, find the angles. For 1.1 you got, for 1 you got, for 5 you got, for 50 you got, and the 100 also you got, 1000 also you got. So you can draw the phase plot. Minus 155 degrees. Both in the same y-axis will be same. You have to mark 155 here. Don't draw separately because these two must be with the same x-axis. You have to draw with the same x-axis. Y-axis only you have to give different scale. That's all. Minus 176 is the maximum value. Now only one simple point I will explain in the next class. But anyhow, how to find the gain margin, phase margin. Here, the phase margin is where it crosses 0 dB. Here it crosses 0 dB. Draw a horizontal vertical line and find the angle. Draw a vertical line and find the angle here. It may be minus, this angle may be minus 165, let us assume. I'm not drawing to the scale, but above 155. Because for phi itself, minus 155. That's why above 155, I know. That's why I put minus 165. Therefore, the phase margin equal to 180 minus 165. That is equal to how much? 15 plus 15 degree. Phase margin is 15 degree. If you insert a phase shift in the feedback path, a 15 degree phase shift in the feedback path, the system becomes in the verge of instability. The system becomes in the verge of instability. Like that, we can find the gain margin. For this sum, the gain margin is infinity. I will explain why later. But gain margin, how to find gain margin, phase margin, we'll see in the next class.